We are looking at page 6 of Unit 7. A ball is thrown upward with an initial kinetic energy of 60 joules. Fill in the blanks. So here we are throwing the ball upward, and it's going to follow this path. I believe in your notes you've got a dotted line showing the up and down motions. So the initial kinetic energy is 60 joules, and this is when you're throwing it from essentially ground level. The potential energy is 0. As it gets halfway up, when the potential energy is 30 joules, remember potential energy and kinetic energy, the sum is constant. We started with 60. Here we have 30 joules of potential energy, 30 joules of kinetic energy. At the top, the potential energy is 60 joules because since it is for one very brief instant not moving, remember at the peak, the kinetic energy is 0. So as it's falling, when the kinetic energy is 12 joules, the potential energy is 48 joules. They should add up to 60 in this particular example. When the potential energy is 15 joules, kinetic energy is 45 joules. And at the very end, at the instant right before it hits the ground, kinetic energy is 60 joules. So in part E, we have a new way to find the maximum height. 0.2 kilogram ball is thrown upward with a velocity of 12 meters per second. How high will it go? So let's draw a picture of what's going to happen. Here's the ball. All right, try this again. There's the ball, and it's basically flying up, and here it is at the peak. At the bottom, we can calculate its initial kinetic energy using the formula 1/2 mv squared. So we know the mass of the object, it's 0.2 kilograms. And we know the velocity, it is 12 meters per second. And that whole quantity is squared. And we have kinetic energy of 14.4 joules. At the very top, the instant that its velocity is 0, we know what its potential energy is because the sum of the kinetic energy and the potential energy is a constant. Here, kinetic energy is 14.4 joules, potential energy is 0. At the top, it should be 14.4 joules. So using our formula, potential energy is mass times the acceleration of gravity times the height. We know the potential energy. We know the mass. We know the acceleration due to gravity. We're looking for h. And so what we have is 14.4 over 2. H, the height is 7.2 meters. So here's a question. Do we have to know the ball's mass to use this method? So let's do this over here. So here's my ball of mass M. Here it is being thrown upwards. Kinetic energy initially, 1/2 times M. We're pretending like I don't know the mass. And 12 meters per second squared. 12 meters per second quantity squared. And the kinetic energy is going to be 72 times M, 72 times the mass. So the potential energy, mass times the acceleration of gravity times the height, we know the total energy. So at its peak, the potential energy should be 72 times the mass. Here we have mass times acceleration of gravity is 10 meters per second squared, and the height is h. So the mass will cancel out. That's 72 divided by 10. It tells me that the height is 7.2 meters. Same answer. The mass didn't play into the calculation, and that's because the mass is the same when it has the initial kinetic energy. The mass is the same when it is at the peak with its highest potential energy. So we don't have to know the mass for this method to work. Jerry, who has a mass of 50 kilograms, climbed a slide with a height of 6.0 meters, sent some dusty sand down ahead of him, and sat on some waxed paper in order to reduce friction, creating a closed system here. Calculate how fast Jerry will be traveling just before impact if he slides down this frictionless slide. So let's draw a picture here. This is going to be the slide. Here's the ladder. There's the slide. The height, 6 meters from top to the ground. Here's Jerry at the top. Here's Jerry at the bottom. Can we calculate how fast he will be traveling? So at the top, we can calculate Jerry's potential energy, mass times the acceleration of gravity times the height. We know Jerry's mass. We're going to use 10 meters per second squared for gravity acceleration, and the height, 6.0 meters. So Jerry's potential energy at the top is 3,000 joules. So if we want to know his kinetic energy at the bottom, we're going to put this number in for the kinetic energy at the bottom. This is the point where Jerry has no potential energy left. It has been converted to all kinetic energy. Kinetic energy is 1/2 times the mass times the velocity squared. So 3,000 joules equals 1/2 times Jerry's mass is 50 kilograms. And we are looking for his velocity. So solving, we find v squared equals 120. Square root of everything says velocity equals 10.95 meters per second. Another question, how fast would Jerry be traveling if he just jumped from the top? So using an older formula, velocity squared equals twice the acceleration times the distance. Acceleration of gravity 10, distance is 6 meters. So we have v squared equals 120 meters squared per second squared. Velocity equals 10.95 meters per second. Compare these numbers. So let's comment on the wisdom of trying to eliminate all of the friction from a slide. Ask yourself, would I jump from here?